Buenos días. Eh, bueno, hoy vamos a comenzar esta sesión. Soy Carolina Gurto, soy investigadora postdoctoral en la Universidad de Chile y hoy tengo el agrado de presentar a Paola Cunha eh, con su charla sobre Simulation of Potentially Habitable Environments on the Surface of Exoplanets. Bienvenida.
Hello, everyone. I'm Paola Cunha. I'm a master's student at the Valongo Observatory in Rio de Janeiro, Brazil. And today I will present you my research, simulation of potential habitable environments on the surface of the planet. My advisor is Luengezi, and here you can see our collaborators. Okay, so let's start talk about potentially habitable exoplanets. The exoplanets of this list follow some criteria. For example, similar Earth mass and radial, and they also are in the habitable zone, which is the ideal distance of the exoplanet from its star, where it is possible to have liquid water on the surface. The first exoplanet, Proxima Centauri b, is the closest exoplanet to our solar system. It has mass around 12% larger than the Earth mass. It was discovered by radial velocity method and was confirmed in 2020 by Suárez and collaborators. Okay, so all of those exoplanets in this list were found around M dwarfs, except of the two ones that I highlighted here. But what about M dwarfs? M dwarfs are low mass stars with mass around 0.08 to 0.055 solar masses. They comprise around 70 to 75% of the solar neighborhood, and also they are interesting to study exoplanets. But M-dwarfs can be more frequently than our sun flares. In this event, the star emits a large amount of radiation, including UV radiation, and UV radiation can be important to life. For example, the vitamin D production in the human body, but excessive exposure can lead the cells to oxidative stress and nucleic acids damage. So considering all those features of flares of M-dwarfs, we can make the question, can life survival on these conditions? To try to provide data to this question, we perform experiments at the laboratory with extreme conditions of UV radiation and gas compositions, and then we use microorganisms to it and then compare our results to Proxima b surface. First, we have to choose our microorganisms. We use yeast, Rhodotorula dairenensis, the species. We call it D23, Diamantina collection site D23. Diamantina is an interesting place in Brazil with some characteristics analogous to Mars, for example, the radiation and the soil composition. And here I have a pic of my yeast in a petri dish. Okay, what about the irradiation experiments? We use two light sources. The first one is a UVC tubular lamp, and the second one is a UV continuous spectrum lamp. But what is the difference? The UV range, you can split it in UVA, UVB, and UVC. So our UVC lamp only it's only UVC, and our UV continuous spectral lamps covers the entire UV. So you have UVA, UVB, and UVC. Okay, the second condition for our experiments was the yeast in saline solution and the desiccated yeast, which is not in the presence of water. And third, we perform experiments in Astrocam, which is a space and planetary simulation chamber, where you can change the gas composition, temperature, pressure, and so on. We use two interesting gas compositions for astrobiology because we don't know the Proxima b atmosphere yet. We use 100% of CO2, which is close to the Mars atmosphere. That is 95% of CO2. And also we use a possible composition for the primitive Earth, 8% of CO2 and 20% of NO2. We decided to keep the Earth pressure. And for that kind of experiments, we used the lamp, the continuous spectral lamp. And our yeast was desiccated. Okay, so just to summarize, we performed 6 experiments. The first group of experiments was the yeast in silent solution. We used the UVC lamp and the continuous spectral lamp. And the second group of experiments was the desiccated yeast. We used the UVC lamp, continuous spectral lamp, Astrocan 100% CO2, and Astrocan primitive Earth. After our experiments, through our results, we used the colony forming units. So here in this pic, we have a plate with my yeast and in the microscope. So every drop here is a colony, so we count the colonies, where there is viable cells, and then we get our results. And our experiments were performed in tubricates. Okay, so let's see our results. First, let's compare the saline solution experiments and desiccated one. Here in this plot, we have the fluence here, and here we have the viability, N per N0. N is the sample irradiated for different values of fluence, and N0 is our control group, so it was not irradiated. The blue and the green curve here are desiccated experiments, and the orange and the purple are the saline solution experiments. So you can see the desiccated keep constant, and we have a steep decrease here for saline solution. A possible explanation for this difference between desiccated and saline solution is because in desiccated, they are not in presence of water, so the metabolic activity is low and they are less sensible to stress factors. Okay, so let's see higher values of fluency for desiccated experiments. The same axis of the other plot. Here we have again the UVC lamp and the continuous spectral lamp. So you can see for the UVC lamp, you have more values of counting than the continuous spectral lamp. A possible explanation for this is because UV, UVB, and UVC are responsible for different kinds of damage. UVA and UVC are more responsible for reactive oxygen species and UVC for photoproducts. Okay, now let's see for our Astrocan results. So this yellowish curve is for Astrocan primitive Earth, and the pink one is for 100% of CO2, and the green, again, the continuous spectral lamp that I showed before. So you can see a difference between the Astrocan and the 100% of CO2. We are not expecting that. And here we have 3 samples irradiated. So we would like to investigate it more to see why, what is happening here. But also you can see that our results for 100% of CO2 is very close to our continuous spectral lamp results. Okay, now let's compare to UVC flux of flares on the Proxima B surface. We don't have much values available for the UVC range. So we used our work of WESH, who analyzed the flares of 52 M dwarfs with galaxies in the NUV band, which is close to the UVC band. And we got an average value of 7 watts per square meter. And for the distance of Proxima B, and Abrefaixa and collaborators also used this value. So here we can compare again the plots that I showed you before. So now we can compare the UVC lamp experiments and continuous spectral lamp for the flare flux of Proxima B. So to our UVC lamp, we have 60,000 joules per square meter, are those that we have counting. And for our continuous spectral lamp, we have counting until 10,000 uh, joules per square meter. So it means that in the UVC lamp case, our yeast can survive until around 2 hours of flares. And our maximum values for a continuous spectral lamp is 24 minutes, which is around typical duration of a flare. So here, in the future, we want to conduct similar analysis for exoplanets and extremophiles. And we also want to investigate the astrokinetic experiments to see why you get that difference. And also, we want to provide important information for the future analysis of biosignatures on the surface of exoplanets. And here I have my conclusions. So we performed irradiation experiments using UVC, UV, and astrochem. You can see the Rhodotorula dairenensis yeast as a potential model to study resistance to radiation. Remember that the UVC range, we do not have it on the surface of Earth. So it's pretty interesting that we have IEC survival at this range. You can see the diamantina potential to study extremophiles. So we studied more extremophiles here in Brazil, and the Proxima B environment can be challenged because here we see a result for a single flare. We should have viable cells that can survive though after flare, but considering frequently flares for M drugs, maybe this can be a challenge. And that's it. Thank you. I'm able to answer your questions about the details that I skipped. And here is my email. So you can email me to make more questions. Thank you.
Thank you, Paola. Questions? No questions? So you mentioned something about extremophiles. Could you tell, could you explain a bit more about this study with that? How you plan to do something related with that?
Okay, about radiation, it's kind of difficult to say, what is a super extremophile resistance to radiation. But I didn't show you, but there is a similar experiment for saline solution using a UVC lamp using Deinococcus radiodurans. I don't know if you guys know it, but it's an interesting module to study radiation resistance. And our values, let me show you. And the value of here, the value of UVC lamp. Comparing, it was very close because it lost 90% of viability close to the 600 value of fluence, and it was very close to Deinococcus radiodurans, and it was a very interesting. Another thing interesting about the study is because the many studies use UVC lamp, which is more available in laboratory and so on. And here we use a continuous spectral lamp, so covering all the UV range. And we also use astrochem, so it's interesting to compare the results that we can see a difference between using a UVC lamp and a whole continuous spectral lamp covering all the UV range.
No questions? Okay. There.
Thanks. So you gave a value for the flags, I think, of the flares. So does that consider the thickness of the atmosphere of the planet?
Thank you for your question. No, it was a condition without atmosphere because it's only a value for the distance of Proxima B, the distance in UA units. So we not consider atmosphere scenario. And what is interesting because this value can be lower for atmosphere situation. And here we have more harmful situation because we're not considering atmosphere. So interesting to see how they could deal with this amount of radiation.
Thanks.
Okay. Last.
Oi, tudo bem? Os laboratórios que você trabalhou ficam no Valongo e eles são da área da astronomia mesmo ou é da área de química? Como é que é?
Oi, obrigada pela sua pergunta. O laboratório que eu usei foi o laboratório da USP. Esse foi os meus experimentos durante a graduação. A minha graduação foi no Rio de Janeiro. Ok. Tá bom. Então, eu fiz os meus experimentos na USP, no Instituto de Química. Lá é um laboratório de astrobiologia e foi muito interessante porque temos astrobiologia, sim, no Rio de Janeiro, mas está a passos um pouco tímidos e o pessoal de São Paulo já tem mais anos de experiência com isso. Então, eu pretendo no meu mestrado agora fazer a mesma coisa no Rio de Janeiro. Então, foi tudo na USP e o pessoal já tinha facilidade com isso. I can repeat in English if you want to. My work, I do it during my undergraduate studies. I performed my experiments at USP, a laboratory in São Paulo. The group there was more, they used to work with it for many years, so they have more experience for that. But I intend to do the same experiments in Rio de Janeiro in the next months or years. That's it. Thank you.
Okay. Thank you for the question. So if you have more questions, please contact Paola after the talk. So the next speaker. Thank you. So our next speaker is Genaro Suárez. He's gonna talk about Brandorf. Yeah, complexity of dust clouds in extrasolar atmospheres. Thank you.
Thank you. Is it okay if I speak in Spanish for all of you? Okay. Bueno, voy a presentar en español. Comienzo por agradecer a los organizadores por este espacio. Mi nombre es Genaro Suárez Castro. Soy investigador postdoctoral en el Departamento de Astrofísica del Museo de Historia Natural, del Museo Americano de Historia Natural en Nueva York. Y voy a hablar sobre una serie de artículos que hemos publicado sobre nubes de polvo que se forman en atmósferas subestelares. Con esta es mi lista de colaboradores. Y bueno, comienzo por mencionar los resultados principales para saber qué esperar en esta plática. Tenemos que para atmósferas subestelares establecemos de manera observacional cómo se forman y cómo se sedimentan las nubes de polvo en este tipo de atmósferas. También reportamos la primera evidencia observacional directa de que este proceso de sedimentación, de evolución de las nubes, depende de la gravedad superficial del objeto. Y por último, reportamos evidencia observacional que la distribución de estas nubes están concentradas preferencialmente cerca del ecuador de los objetos. Entonces, comienzo por introducir estos objetos que se llaman enanas cafés o enanas marrones, dependiendo dónde estamos. voy a llamarlas enanas cafés como acostumbramos en México, y son objetos subestelares que tienen masa insuficiente para sostener fusión de hidrógeno estable en sus núcleos. Como consecuencia de esto, los objetos evolucionan con el tiempo, se hacen más débiles, más fríos y se contraen con el tiempo. Como consecuencia de esta evolución, distintas especies químicas aparecen en sus atmósferas, lo que nos permite clasificarlos en diferentes tipos espectrales que van de las M tardías para las enanas cafés más calientes y más jóvenes. Luego tenemos los tipos L, tipos T y tipos Y para las enanas cafés más frías. Estos objetos, las enanas cafés, es el enlace que hay entre planetas gigantes de tipo Júpiter y estrellas de muy baja masa. De hecho, las enanas cafés comparten propiedades físicas espectrales con planetas de tipo gaseoso. Y un aspecto muy importante, muy interesante de las atmósferas subestelares es que son lo suficientemente frías para formar nubes ricas en química. Podemos encontrar nubes de óxidos refractarios, nubes de silicatos, de hierro, nubes de distintas sales, e incluso se predice que pueden haber nubes de agua en objetos de tipo Júpiter. Estas nubes se forman en lo alto de la atmósfera y conforme la atmósfera se enfría, las nubes se van a capas más internas que llega a un punto donde la nube desaparece de la fotosfera. A ese proceso se le llama sedimentación y, como digo, ocurre conforme la atmósfera se enfría, las nubes se van a capas más internas. De hecho, bueno, este tipo de nubes son comunes en exoplanetas y en planetas de nuestro sistema solar, incluso en lunas de nuestros planetas del sistema solar. De hecho, se cree que las capas más internas de Júpiter están hechas de nubes de silicatos y nubes de hierro, pero no las podemos observar por todas las capas que están arriba. Pero si queremos aprender de esas capas más internas de planetas gaseosos, podemos ir a las enanas cafés más calientes, donde esas nubes están en la fotosfera. Y eso es lo que vamos a hacer en este estudio. Estas nubes de silicatos y de hierro se cree que son las responsables de distintos efectos que se han observado en enanas cafés, como son una dispersión de color que existe para objetos con el mismo tipo espectral o con la misma temperatura. O sea, si observamos enanas cafés con una temperatura muy similar, pueden tener una diferencia de color de hasta más de una magnitud, que es bastante. También la fotometría, la variabilidad fotométrica en estos objetos también se ha atribuido a las nubes de silicatos, a inhomogeneidades que hay en las nubes que al rotar el objeto, pues produce estas curvas de luz que observamos en múltiples artículos. Estos efectos de dispersión de color, de variabilidad, también se ha encontrado que dependen de la inclinación de la enana café. Aquí tenemos que cuando el objeto está inclinado o cuando estamos viendo cerca del ecuador del objeto, el color de esa atmósfera es más rojo de lo esperado. Cuando el objeto se observa cerca de los polos o inclinaciones bajas, es inclinación del eje de rotación. Entonces, para inclinaciones bajas, el color es más azul de lo esperado. Y este resultado es consistente con la idea de que las nubes deberían de estar concentradas en el ecuador, pero no se había reportado evidencia directa de eso hasta, como voy a mencionar en esta serie de artículos. Pero los modelos de circulación general atmosférica, de hecho, predicen que deben de haber más nubes, más cantidad de nubes a latitudes bajas y conforme vamos hacia los polos, la cantidad de nubes disminuye. Entonces, parte de los objetivos de esta investigación fue caracterizar esas nubes de silicatos, sus propiedades físicas, su composición y su distribución. El único rasgo espectral conocido que producen estas nubes y que se ha observado en objetos subestelares es esta absorción en el infrarrojo medio, que va más o menos de 7.5 a 13 micras. Y el único instrumento hasta antes del James Webb capaz de observar de obtener espectros en estas longitudes de onda fue Spitzer. Y hasta antes del trabajo que estoy presentando se conocían 5 objetos con esta absorción. Pero nosotros nos dimos cuenta que en el archivo de datos de Spitzer habían más espectros con esta absorción. Y lo que hicimos fue reprocesar todos los espectros de Spitzer, todos los espectros infrarrojo medios de enanas cafés. Y aquí muestro una colección de unos pocos de estos espectros, donde vemos distintas moléculas. Tenemos agua para todo el rango de enanas cafés. Tenemos también metano, amoníaco, y tenemos también los granos de silicatos para enanas cafés relativamente calientes. Y en este rasgo es en el que me voy a enfocar. Entonces lo que hicimos fue definir un índice para saber qué tan profunda es la absorción en los espectros. Le llamamos el índice de silicatos, que es el cociente entre dónde debería estar el continuo y dónde realmente está el flujo. Entonces, este cociente nos dice qué tan profunda es la absorción. Aquí en esta figura comparo los índices para toda la muestra como función del tipo espectral. Y vemos pues esta forma que en la ausencia de la absorción, en la ausencia de esta absorción, deberíamos de esperar que el índice disminuya conforme con el tipo espectral. Sin embargo, observamos este pico que nos indica que aparecen aquí las nubes de silicatos para estos objetos. Analizando este pico, obtuvimos cómo se forman, cómo se hacen más gruesas las nubes y después cómo se sedimentan en un rango de temperaturas entre 2000 y 1500, 1300 Kelvin. En esta ilustración de una nota de prensa de la NASA sobre este resultado, resumo es lo que platico, que tenemos que cuando la atmósfera es muy caliente, no se pueden formar los granos de polvo. Cuando la atmósfera se enfría un poco, aparecen los primeros granos de polvo, luego se hacen más gruesas esas nubes de silicatos, pero eventualmente desaparecen de la fotosfera. Siguen estando en la atmósfera, pero ya muy profundas. Y esto representa, esto establece por primera vez cómo se forman y cómo evolucionan estas nubes de manera directa. Luego también comparamos cómo la absorción de silicatos, cómo depende con la variabilidad de los objetos. Y aquí tenemos la curva similar a la anterior, pero enfocándonos en los objetos que se conoce que son variables en rojo y los que no son variables en azul. Y hay una preferencia por los objetos variables a ser ricos en silicatos. Son aproximadamente 2 veces más probables los objetos variables de ser ricos en silicatos. Este resultado se alinea con la idea de que estas nubes de polvo son las que producen la variabilidad en enanas cafés. No es definitivo todavía, pero apunta en que sí son en efecto estas nubes las que producen la variabilidad. En un trabajo posterior, comparamos cómo cambia la absorción con la gravedad superficial de los objetos. Y lo que muestro en esta figura es una muestra de objetos jóvenes y objetos viejos que tienen la absorción y una muestra de objetos que no tienen la absorción, que nos ayuda a saber dónde debería de estar el continuo. Usamos esta muestra de objetos sin la absorción para remover el continuo y obtuvimos estos perfiles. En azul tenemos el promedio de los objetos viejos y en rojo el promedio de los objetos jóvenes. Como vemos, hay algunas diferencias claras, incluso dentro de las incertidumbres, y las diferencias son que los objetos jóvenes la absorción en los objetos jóvenes es más roja, más ancha y más asimétrica. Esto nos dice que la absorción de silicatos es en efecto sensible a la gravedad superficial. Lo que nos preguntamos es qué es lo que produce estas diferencias. Y comparamos estos perfiles. Esto es el inverso de los perfiles, simplemente para comparar con predicciones teóricas. Tenemos modelos que predicen cómo debería de ser el rasgo para distintos tipos de granos con distinta química, con distinto tamaño. Y lo que encontramos es que la forma de la absorción para objetos jóvenes en rojo, el único tipo de granos capaz de reproducir la simetría que se observa son granos hechos de silicatos ricos en hierro, con tamaños del orden de 1 micra. Aquí enfatizo que son silicatos ricos en hierro porque hasta el momento no se ha incorporado este tipo de granos en los modelos, pero al parecer por las observaciones más recientes de James Webb es necesario incorporar este tipo de química más compleja para reproducir las observaciones. La absorción en los objetos viejos es mejor predecida por silicatos más comunes, pero más ligeros. Entonces lo que tenemos es que una atmósfera joven está hecha de granos más pesados, una atmósfera vieja de granos más ligeros, y eso dice que la sedimentación depende de la gravedad de los objetos. En este artículo más reciente aún, tenemos lo que yo considero el resultado más importante de esta serie, que es que comparamos cómo la opacidad de las nubes depende de la inclinación del objeto. Tenemos que cuando el objeto se observa cerca del ecuador, vamos a ver una absorción más intensa o más nubes. Cuando se observa cerca de los polos, vamos a ver una absorción más débil o menos opacidad. Y esto también se correlaciona con el color de los objetos, donde los objetos más rojos están vistos del ecuador, los más azules vistos de los polos. Y esto pues nos ayuda a entender la apariencia de las enanas café, por qué vemos distintos colores. En esta figura resumo lo que mencioné. Tenemos que para una atmósfera, cuando la vemos cerca de los polos del ecuador, vamos a tener una absorción intensa y un color más rojo de lo esperado. Si la vemos a la misma atmósfera de una latitud más arriba, vamos a tener una absorción más débil y un color más normal. Si observamos cerca de los polos, la absorción básicamente desaparece y vemos un color más azul de lo esperado. Esto es importante también para entender la diversidad espectral de los exoplanetas, no solo de enanas cafés, por lo que vamos a participar en una conferencia de prensa en la próxima reunión de la Sociedad Astronómica Americana. Y todo lo que he mencionado es con datos de Spitzer, pero también tenemos programas aprobados que ya nos están dando datos con James Webb, con MIRI, para investigar más a detalle la formación, evolución y la química de estas nubes, para entender la distribución latitudinal en atmósferas jóvenes, para saber si realmente son estas nubes las que producen la variabilidad. Y pues hay otros objetos con nubes que se han encontrado en el ciclo 1. Y pues en esta lámina resumo lo que mencioné aquí de manera poco rápida. Tenemos evidencia directa, observacional, para distintos aspectos de nubes de polvo en atmósferas subestelares y de tipo Júpiter. Tenemos resultados sobre cómo se forman, cómo evolucionan, cómo es su composición y qué efectos tienen estas nubes en las atmósferas. Y por último, cómo se distribuyen de manera latitudinal. Muchas gracias por su asistencia.
Muchas gracias, Genaro. Tremenda charla. Tenemos tiempo para 2 preguntas muy breves. Vamos.
Hi, thank you. This was very interesting. Could you go back to the slide where you show the normalization, the continuum? Because I know it's a very tricky business to normalize the spectrum of such a cold
This one,
stars.
right?
No, like the first one. Yeah, you can do this one.
Okay.
I just want to know, how did you select the 2 points of, I don't know, it seemed like you selected 2 points of true continuum, but I want to know more about that because the normalization can change everything. So this is my
Exactly.
question.
There are 2 reasons.
You can answer in Spanish if you want. It's
Okay. Entonces aquí hay dos razones principales para seleccionar estas regiones para remover para caracterizar el continuo. Por un lado, para la parte de las longitudes de onda largas, lo que consideramos es alejarnos lo más posible de la absorción, pero tener cobertura espectral. No podemos ir más allá de 14 micras, que es donde llegan los espectros de Spitzer. Sin embargo, la absorción para objetos viejos se termina más o menos a 11.5 micras. Pero eso es solo para objetos viejos. Para objetos jóvenes, la absorción se alarga cerca de 13 micras. Entonces, movimos el continuo lo más lejano de la absorción para que sea representativo de objetos jóvenes y viejos. En la parte de longitudes de onda cortas, lo que hicimos es buscar un equilibrio entre evitar la absorción de agua y estar fuera de la emisión de silicatos. Entonces exploramos mover esta región y fue la que mejor resultado nos arrojaba.
Sí. Quizá la pregunta que tengo es muy básica, pero quisiera entender bien. Lo que está ahí representado, ¿ese es el espectro de emisión de la radiación propia de la enana café?
Correcto.
Y el espectro de reflexión, o sea, la radiación que viene de la estrella central y se refleja en el planeta, ¿juega algún papel cuando uno hace la observación?
En este caso, no, porque la mayoría de estos objetos están aislados. No están alrededor de una estrella, que de hecho es la ventaja principal de estudiar enanas cafés para aprender de exoplanetas, porque no tienen una fuente brillante cerca que dificulte la observación. Entonces, la mayoría de las enanas, de los espectros que menciono son de objetos aislados. No hay nada que contamine.
Gracias, estamos un poco tarde con el tiempo, así que gracias, Genaro. So the next speaker is Henrique Reggiani. Please go ahead.
Hello, good morning, everyone. Thank you for having me here. So I'm Henrique. I work currently at NORA Lab, Gemini South. And I'll talk a little bit about stars and a little bit about planets. So we'll start with stars. So I like to study stars that are kind of FGK stars, effective temperatures 4,000 to 6,500. This kind of log Gs, because when you get out of that, things start getting more complicated. And while we are in that range, we can have really nice data, really nice stellar spectrum like that, in which you can measure basically any type of chemical elements you want, from lithium all the way to neutron capture elements. So I'll just give you that information to keep that in mind as we go. So what about planets? I said a little bit about stars, a little bit about planets. So a little bit about planets that I want to talk today about is how exoplanets are formed. We don't know exactly the formation processes. It could be pebble accretion, it could be core accretion. But one interesting prediction that was put out by Oberg in a very simple model that they worked on is that depending on the carbon to oxygen ratio that you see in a planetary atmosphere, you can have an idea of where in the planetary disk the planet was formed. So we have a star here, and this model is basically for the sun. And as you go farther away into the disk, things get colder and colder, and you have ice lines. So first you start by freezing out water, and then at some point you start to freeze out CO2 and eventually CO. So as the ratio between grain and gas change, it will change the composition of the atmosphere of the exoplanet if the exoplanet was formed here or formed here or formed here. Okay. And there are some predictions for how it should look like. Now, we need to know something about the disk where the planet formed if we want to make this type of conclusions. And here's just an example of how abundances in disks that we can actually observe in the solar neighborhood change. So you have different carbon, different nitrogen, different oxygen abundances in different disks. Unfortunately, when you are observing a planet, when you're observing a star, most of the time, the disks are already gone. You can't actually make any measurements of disks for most of the stars and planets we're interested in studying. So what you have to actually do is to look at the star, because the star is the remnant, it's which contain most information about the disk, where the star, and therefore the planet that's orbiting the star formed. And here is an example of the chemical composition, actually the carbon to oxygen ratio of stars in the solar neighborhood at solar metallicity. And I want to show this because typically for exoplanet studies, the current assumption is, well, these are very close to us, they're in the thin disk, they're in the solar neighborhood, so the stars should have solar carbon to oxygen ratio. But when you actually look at the distribution at solar metallicity, the mean carbon to oxygen ratio is different than solar. While the sun has a C2O ratio of about 0.49, we see that the mean ratio here is around 0.58 dex. And let's ignore this for a moment. So now we know we can't measure the disks because the disks have dissipated. If we assume solar composition, then it's probably incorrect because most of the stars in the solar neighborhood don't have solar carbon to oxygen ratio. What do? Well, you look at the actual star, right? But some cases, like the case of Beta Peak, which is the planet I'm interested in talking about here, Beta Peak is this star over here in blue. So it has an effective temperature of 80,000 Kelvin, log G of 4.22, and very importantly to this discussion, rotation of 113 kilometers per second. So even if you have exquisite spectral information, like this blue spectrum here, which is HARPS data, signal to noise of around 250 at this region, and a resolution of 115,000, this is what happens with this tiny carbon feature that you can see in another star in Beta Peak. You just can't measure atomic features. And to this day, there is no oxygen measurement in Beta Peak at all. So this means that people that are analyzing Beta Peak B, the planets around Beta Peak, so far, they had to rely on the assumption of solar abundance, just because we can't measure them in Beta Peak. Okay, so you can't measure them in the disk because the disk is not there. If you assume solar, you might be doing it wrong. You can't actually measure it in the star. Well, what do? Stars are formed in clusters. Stars are never formed alone. And if you actually look at young open clusters, you'll see that the abundance scatter from star to star in clusters are on the order of 0.02 to 0.03 dex. So they're extremely homogeneous. And to the purposes of what we are doing here, an uncertainty, a scatter of 0.02 in between stars is pretty much okay because our uncertainties are typically larger for carbon and oxygen abundances. So what if we look at a star that was formed with Beta Peak at the same molecular cloud and use that as a proxy to study the molecular cloud from which that planet was formed? Currently, Beta Peak is not in any known open clusters, but it's part of a moving group. That's the reminiscent of an open cluster. And this is what Beta Peak's moving group looks like in the sky. So we went to this work, mid-Agroi 2020, and we looked at all the moving group members of Beta Peak. And as you can see, out of the 26 members they identified for this moving group, 22 are M stars. as we just heard in the last talk, it gets complicated as you go colder and colder. There are only 2 stars for which the type of analysis we wanted to make is possible, and for which carbon and oxygen can be, it's more amenable to the analysis of carbon and oxygen abundances. Unfortunately, one of those 2 stars is also rotating too quickly. It's about 50 kilometers per second, and the carbon lines there just don't exist. So our analysis is based on the abundances of HD 18, 13, 27, the only star in the moving group for which we could reliably measure carbon and oxygen atomic features. And that is important because only for atomic features, we can do non-LT and 3-dimensional corrections. So we did all that. We measured 18, 13, 27. We have a non-LT abundance metallicity of 0.13 and a carbon to oxygen ratio 3D non-LT of 0.62. Okay, what do we do next? I show the difference between beta peak abundances, the abundances that actually have been measured, to the abundances of HD 18, 13, 27. And I only want to show this to reinforce that while clusters have abundance differences on the order of 0.02 DAX, the difference between these 2 stars is as high as 0.5 DAX, which means that the differences, they do not come from the usual scatter that we see in star formation processes. It comes from the fact that beta peak has different stellar properties that doesn't allow us to use it as a good proxy for the formation of the planet itself. Okay, now let's go back to the planet really quickly. And what I want to talk about the planet is that, well, there's the JWST data for this planet. So I got the data. We reanalyzed the data. Previous analysis of beta peak B was done by the gravity collaboration. They found temperature of 1500 Kelvin and a metallicity of 0.5. And a metallicity of 0.5 for a planet that is about 10 solar masses-ish, it's just too high. For the formation processes that they concluded beta peak B had, it's extremely difficult to explain this type of metallicities. But when we redid the analysis with some improved pipeline for the data reduction, and that's important to say, we actually find that the planet has a metallicity of 0.08, which is extremely close to the metallicity we found for HD 18, 13, 27, which we are using as a proxy. So what actually happens when you put the new information about the planet and the information about the new star together to try to analyze how this planet was formed in light of the model proposed back in 2011 by Oberg and collaborators? Well, you can build a plot that is like this. It is based on their models, which basically means each one of these quadrants has implies a different formation location and a slightly different formation process for the planet. And now let's put our data in these plots, which is the thing that we have been trying to do. So if you use gravity collaboration measurements of the planet and solar abundance, this is what you get for the star. And if you use our improved abundances, carbon to oxygen ratio for the planet with solar composition for the star, C2O ratio, this is what you have. And both analyses agree that you have formed the planet outside the ice line, and after the planet was formed, you had a lot of accretion of icy planetesimals to explain the abundance of oxygen, the relative abundance of oxygen that we see between planet and star. We are also very happy that if we actually use the stellar abundances of HD 18, 13, 27 as a proxy, we also find the same results regardless of the gravity collaboration carbon to oxygen ratio or ours. Now, what I want to say about this is very important because we didn't expect the results of the gravity collaboration and ours to agree at all, because they're based on different data analysis and different assumptions for both the planet composition and the stellar composition. So this is actually very strong evidence that we have for where and how this particular planet was formed. And in particular, the most important part is that after it was formed, its envelope accreted extremely large amounts of icy planetesimals. And I just want to point out that it should be order of 200 to 300 Earth masses of planetesimals being accreted after formation of the planet. And I will finish with that and leave you with my conclusions. Thank you.
So we have time for questions. So over there, please. Well, first.
Thank you. Very, very interesting talk. However, I am worried because I think that conclude where the planet formed, considering the measure of the abundance of the planet, could be a tricky question, because we know that planets migrate in the disk, and the migration of the planets along the disk could change this abundance. And moreover, there are new works, for example, for Bertrand Beach, that show that when you include the evolution of the dust in the disk, the dust can sublimate in the different ice lines. You can accrete, for example, carbon or oxygen in form of vapor, and you also could change the abundance of the planet. So I don't know if you can say that the planet formed in some position just looking on the abundance of the elements.
Yeah, absolutely. You are totally correct that our assumptions are based on a very simplistic model, doesn't account for chemodynamics of the disk itself. It's a first approximation result. Yeah, you're correct about that. But what's interesting is that the 2020 paper by the Gravity Collaboration that studied this, they went a lot deeper than we did in the actual formation processes. And they accounted for some chemodynamics, not everything that's available in the literature, but they did account for that. And their conclusions were basically the same as ours for this particular planet, which is mostly because of the extremely high abundances of oxygen that are what is driving the low abundances of the low carbon to oxygen ratios. But we can talk about more of that later if we want to.
Oh, nice talk. I would like to know what kind of clouds do you incorporate in your modeling to reproduce the near spec spectrum that you show?
Oh, I wasn't the one that made the planetary analysis, so I have to check the paper. I'm sorry, I don't have that in my head, but we can talk later. I can show you.
Thank you.
Okay, let's send again Henrique. Our next speaker is Yamila Miguel. Talking about the next generation of models for giant planetaries.
Hello, everyone. Good morning. I'm Yamila Miguel from Leiden in the Netherlands. I'm also originally from Argentina, but I will give the talk in English because I think it will be better for everyone here. So today I will be talking about interiors of exoplanets. Yeah. But first, why we care about interiors, and especially of exoplanets that are so far away and we don't have such a good data, for example, as with solar system giants. The thing is that giant planets are the first planets that are born in a planetary system. And for that reason, really, they have key information in their interiors and their atmospheres to understand those first processes, as we just heard, for example, in the previous talk. Now, particularly, what I would like to know is what are the bulk metallicities of these planets, because these help us to understand more about the formation process of giant planets that we know so little. And I would also like to know how are those metals distributed in the interior. And this is really key, because now that we are getting more and more information and our models are getting better, it's not the same if we have a planet that has a core of 30 Earth masses or 30 or 10, right? It implies a different formation process. So really, we need to start learning more about the interiors of planets and not only remain with the information that we get from their atmospheres. Now, I'm talking about the next generation of interior models for exoplanets. And let me tell you why I'm thinking that we need to step up our game on the modeling that we are doing. The first thing is the information that we are getting from the giant planets in our solar system. So we have very detailed data for Jupiter, for Saturn, because we just actually had missions there that help us to map the gravity fields and improve our interior modeling. And this is more or less how the interior of Jupiter looks like, our best knowledge of the interior of Jupiter. So we think that it has a core, here, made of 100% heavy elements. But is this picture that we used to have, that the core was separated from the envelope, and then we have a fully convective envelope, is kind of breaking down these days. We think that there is a gradient of metals going from the core to the outer parts of the planet. And that would imply that actually the metallicity that we measure in the atmosphere does not represent the metallicity in the whole planet. So we really need to think about this as well when we are interpreting results from atmospheric measurements. Now, we are not getting this information only for the giants in the solar system, but also some interior and formation models for giant exoplanets are finding these inhomogeneous structures naturally from the formation process itself. So then we have to really start thinking about what happens when we don't have fully convective envelopes anymore. And finally, why we care about this now is because now we are getting great data, and we are going to hear more about this in Rodrigo's talk later this afternoon, about all the amazing information we are getting from JWST. So then we are not only getting masses and radius for exoplanets, we are also getting way better abundances in their atmospheres. So then the question is it possible to take all this information and learn more about the interiors of these planets or not? So let me tell you a little bit about what are the models that we are using these days. So this is really our interior model, current interior model for exoplanets. Most of the papers out there that are modeling interiors, exoplanets look more or less like this. They have a compact core made of 100% metals, and then they have this convective envelope that I mentioned before, where all the material is well mixed and homogeneous. And of course, this means that the abundances that you measure in your atmosphere represent more or less the bulk abundances in the planet. And that's why we are thinking on this picture of, or the CO ratio might tell us where the planet was born, because we think that everything is well mixed. In reality, planets probably are more or less like this. It looks the same on the screen, but there is a gradient, or I try to put a gradient of metals here, which means that the metals that are here in the compact core, they go towards the atmosphere with a gradient. So then we are not completely sure if the atmospheres are completely convective or not, and where they change. So this is something that we need to further investigate. All right, so in order to study this a little bit more, and also to know if it was possible to learn a little bit more about the interiors of exoplanets with atmospheric measurements, we make a retrieval model for interiors of exoplanets. And this is work done by my student, Sane. I put her picture there. And basically what we start with the observational constraints, mass, radius, and if we have atmospheric measurements, then we have an interior model that we took actually from interior models for Jupiter and Saturn. And then we do a Bayesian model. So basically we don't run one model, We run hundreds of thousands to see which ones fit the observational constraints better. And then what we get out is the mass of metals in the envelope, the mass of metals in this dilute core region, the core mass, and the bulk metallicities of exoplanets. So let me show you some of the results that we are finding. But first, we did a test with one planet that we created. We knew which was the core mass, where was all the mass distributed, and we just simulated observations and tried to see if we could retrieve the core mass that we knew the planet had for that test planet. So then you can see here the result. So this line here represents where is the core mass, or where should be the core mass. And we are showing results with our models of a homogeneous planet and also an inhomogeneous planet. And you can see that when we are using as constraints only the mass and the radius of the planet, that this is basically what we had so far, then it's not possible really to tell which is the core mass. And this, of course, makes sense, right? We have way less observational constraints than the data we can get out. So, of course, we need more observational constraints to actually get more information from the interiors of the planets. So then we said, okay, what happens when we add also atmospheric metallicities, equilibrium temperatures, and helium abundances? And then when we do that, we are actually able to retrieve the core mass of the planet that we knew it had with both models, with the homogeneous and the inhomogeneous model. So then this really encouraged us to actually go and try to find core masses and distribution of elements for exoplanets, for real exoplanets, and not just a test one. And we did this for a sample of 32 exoplanets, all giants, all of them with atmospheric metallicities measured. But this study that we did was before JWST results, so also the error bar were huge. So just bear that in mind. We are trying to make that better now with the new results we are getting. All right, first thing that is important is that atmospheric metallicities really help us, or will help us in the future, to constrain interiors of exoplanets. So this means that we can now start trying to learn a little bit more about the interior structure of these objects. This is the result that we are finding for the sample of 32 exoplanets. And here we have the total metallicities that we retrieved, bulk metallicities, and here is the total mass. So there is this relation between the metallicity of the planet and the mass of the planet that was studied in the past. So we are not the first ones really to do that. And what you can see here are the red dots are Jupiter here and Saturn. And you also see two different colors because those are the results of the two models we use, the homogeneous and inhomogeneous. You see that actually the answers are different. So really it matters where we put that material in the interiors of the planet. You also see huge error bars. And this is also because the data that we use have huge error bars. I hope that now that we are getting better metallicities or more constrained metallicities with JWST, we could also learn a little bit more about this. And we see that there is a kind of a relation here between the metallicity and the mass. There are a few outliers, like these two planets here and this one here. This one that you see here is a very massive planet. It's also very inflated, and probably our model doesn't work very well with it. So we kind of discarded that one. For these other two, we were studying what about the metallicities of the stars. And when we did that, so what you can see here is the metallicity of the star. And you see that actually these two planets that are more metallic, their stars have also higher metallicities. So this is maybe something to study in the future. It was also investigated in the past and they found no correlations, but maybe now that we have better data is something to think about. We are also finding distribution of metals because this is what I told you at the beginning that we wanted to get out of this. And what you can see here is, again, the metallicity, but you see how this metallicity is distributed in the interior. So here is the core of the planet, and here is the atmosphere. And you see that first we have 100% metals in the core, in the inner cores, and then there is a gradient of metals going to the outer parts of the planets. So this is what we are finding with our inhomogeneous models. And on this other side, I'm showing core masses that we retrieve. This is, again, that planet that was supermassive, so we are not taking this one into account, but we are getting core masses for all the others and also metal mass in the envelope, for example. So we are starting to learning a little bit more about this. Not all of them have the same core mass, and most of them have core masses less than 30 Earth masses. So this is also something that we can take on our formation models. Okay, I will leave here with a few conclusions. I think that the most important take-home message is that with the new data that we are getting, and it's amazing data, we can really start thinking of improving our interior models and learning something about the interiors of exoplanets. The second one is that there might be a dependence with the stellar metallicity. I think it's something that maybe needs to be revised. And the last one is that not all planets have the same core mass as we used to do in the past. This matters definitely for finding different results for the metallicities of the planets. And I would like to thank you for your attention.
Thank you very much, Yamila. Questions?
I'm wondering where the regime to use interior and atmospheric model is. For example, because I see measurements from the atmosphere, so just to know, like, yeah, where is the regime between those models?
So the atmospheres are just a tiny, tiny, tiny percentage of the entire planet, 1% or something like that of the radius. And basically what happens in the atmosphere is that you have that external layer. So then at the very bottom of the atmosphere, the material is mixed. Chemical equilibrium explains the abundances very well. When you go higher up, you probably have mixing, condensation, mixing not only vertical, but horizontal. You know, these planets rotate. So all those things will affect the atmospheres, that the abundances that you observe. And we cannot say that the ones that we observe are really the ones that are deeper down, and definitely not the ones that will go all the way to the center of the planet. So here in this model, we basically start the model at this boundary between the atmosphere and the interior.
Hello, very nice talk. I have two questions. One, I noticed that you put an energy source in your equations. Are you using something? That is one question. The other one, how you model metals, equation of state, what is the effect, if you can comment on that?
Yeah, so these are all static models, which means that we don't model the evolution. So then we actually retrieve the luminosities of the planets as well, and that is our internal energy. It's one of the retrieval parameters that we get out. The second one for the one thing, though, is that we tested with evolution models, and actually it works very well to retrieve luminosities as well, which was surprising. I had little faith on that, but it's kind of a different kind of model as well than the one that has been done for exoplanets before. The second one with the metals, we use, equations of state for ices and rocks, mix of ices and mix of rocks. At the moment, we are using the Sesame one, but I think that the next thing will also kind of get better on that. So I know that there are new equations of state for ices, particularly. It doesn't matter that much in these ones that are so massive. Mostly hydrogen and helium is what matters. And we tested different ones for those ones as well. So I have other results if you are interested.
Hi. Is there a reason you use aggregated metallicity instead of abundances from different elements, or is it just practical thing, or?
Is practical. So when you go to the interior, the planet has 80% hydrogen and helium, the rest are metals. So it doesn't matter that much for the interior modeling. So if you have more water or CO2 or CO, for us, it's all ices and all the same. Also because we just don't have enough equations of state of all of these things at the pressures and temperatures that we need. So we kind of mix everything up. And another reason is that when you go very deep to very high pressures, all those molecules just mix, they make a fluid, sometimes a metallic fluid. So it's not that they remain in the same state as when they go deeper down.
Thanks again, Yamila. So our next speaker is Aline Novais. with the effects of pressure dependency in exoplanetary atmospheric retrieval. Thanks. Where's the All right. Hi, buenos dias. I'm sorry, but today I'm going to be talking in English. So my name is Aline Novais, and I'm from the Federal University of Rio de Janeiro. I'm basically finishing my PhD now, and I'm going to talk to you a little bit about retrievals in exoplanet atmospheres. So here I'm trying to summarize how retrieval works, actually how characterizing atmospheres work. So as you probably know, we can do a lot with the, oh my God, with the transect technique, which you probably know. So we can observe the planet when it's passing in front of its star. And if the planet has a significant atmosphere, we can try to infer what this atmosphere has. So if we observe it, we can obtain what we call a transmission spectrum. Of course, we have different kinds of spectra, but this is the one I'm working with. So, and then if we analyze this kind of spectra, we can try to infer some atmospheric information. So for example, what is the composition of this atmosphere? What is the pressure temperature profile? Some information about whether they have clouds or not, and etc. And this is just an example of how my retrievals work. So basically, when I talk about retrieval, for those of you who don't know, we're using observed data. So data, in my case, from Hubble. And we're trying to fit different atmospheric models to this data to see basically which one works best. And this is how we will try to characterize these atmospheres. So in my work specifically, I work with a sample of 38 exoplanets. Most of them are gas giants, but not all of them. And as I said, I work with transmission spectra for these planets. And we use a Bayesian asset sampling approach, which is kind of similar to MCMC with some differences. And well, yeah. So for the methodology, I'm going to explain to you a little bit how my code works. And my code is based on a code developed by Fisher and Hang in 2018. So I basically took this code and updated it in my own work. So for the original code, we have some assumptions that we have to make, of course, to try to infer these atmospheric parameters. So we are basically using constant temperature and pressure instead of a whole profile. And of course, we have hydrogen and helium as background gases. And we also have the option to include some additional molecules and also clouds as well. And some different effects in the atmospheres, which I'm gonna go into in bigger details. So this is kind of a scheme to try to show how they work, how the models work. So here I'm representing different models, and they start to become more complex as we're adding some more parameters to the models. So we can add parameters, for example, extra molecules or clouds, and we try different type of clouds. So we can try gray clouds, for example, with a constant opacity, and we can try non-gray clouds, which would be inhomogeneous clouds. And as I said, we're using a Bayesian inference approach to try to determine which is the best model for that specific atmosphere. So now about my specific work that I developed during my PhD. So we took the original code, Helios-T, and we tried some new features. And here I highlighted sorry, I think this doesn't really work, but I highlighted the main features that we added to our code. So basically, Rayleigh scattering by hydrogen is going to be important. But most important than that, we tried, instead of a constant pressure, we tried to do a code that known as a variable code. So our opacities are going to be varying with pressure. And then we're going to see exactly
why we need pressure in these atmospheres. Here is also a summary of the main opacity sources that I'm using. So basically, chemical species like absorption, scattering and stuff, clouds, which are usually very, very important, but for my data, they're not going to be as important. I'm going to show you why. And features like radiation scattering, as I told you, and collision-induced absorption, which I'm going to be calling CIA. Just for you to understand exactly how my non-isobaric treatment works, it's because we're going to analyze the atmosphere in two ways. So we're going to see basically in the picture, in the horizontal way and in the vertical way, which would be like, if we're looking at the planet, we're going to see the transit chord and we're going to see the altitude. So we are developing the code based in two different measurements. And also the opacities that I just told you about, they're going to be pressure dependent from now on. So we're going to see how important is that. So first of all, for the statistical results, as I analyzed 38 planets, I tried to look at them all at once to see if they have any trends. And the most important thing that we notice is that most of them are best represented by cloud-free or gray cloud atmospheres with water only as the main absorber. And that's probably not like physically accurate. That's probably because of our data, the data we're using from Hubble. As Yamila said in the last talk, like the uncertainty bars are very big, so we can't really do a lot with that. And this is gonna become much better in the future. And also, of course, no evidence for extra molecules because we are looking at a very narrow range in the infrared. So we only have water features there. We can't really see other additional molecules. And also here's a summary for these 38 planets. Of course, they're not all here because some of them are flat lines and outliers and etc. But here we try to analyze what would happen if we include or not include different effects. So here I tried basically Rayleigh scattering and CIA, which were the most important for us. And one thing that you have to keep in mind is that CIA is very pressure dependent. So I'm gonna show you later. So as we added pressure in our code, we saw that basically CIA that was in the code before became much more important because now pressure is actually varying. So here, if you look at all of them at once, you can see that the models that include CIA are a little bit more accurate. So the error bars are a little bit smaller, okay? But of course, it's not that much. And then we took two case studies, so two planets that are very well known to try to understand in deeper this effect. So here I show you our retrieved spectra and our retrieved water abundances in the right. And I show you also isobaric versus non-isobaric abundances. So this would mean constant pressure and variable pressure. So basically, if you look at the spectra, you see that when we don't include Rayleigh and we include Rayleigh, things become different. So we have like a Rayleigh slope on the left side of the spectrum close to the optical range. And in this data, this is very important because WASP-12b was the only planet in our sample which has a little bit more data more to the optical side. So Rayleigh is very important in this case. And you can see when we include Rayleigh in the case, the CIA, which is also there, is gonna kind of mute the Rayleigh features when we go to the non-isobaric case. I mean the pressure case, where CIA is actually working. So the water abundance there on the far right is gonna vary a lot. So it's gonna become higher. And then for the second case study, which is for HDT09, the opposite is gonna happen because it doesn't have a lot of data to the left side. So CIA is gonna become more important and Rayleigh is not as important in this case. So you can see in the far right picture that the water abundance is gonna vary a lot when we include pressure dependency because of CIA again, because you're gonna have this continue in the spectrum, like a continue like this, and then the water abundance. To finish up, we also notice some degeneracies in our results. And this is basically, as I said, due to the fact that we're using Hubble data. So of course, things are not gonna be as accurate and as constrained as they should be. So we're gonna see, for example, degeneracies between temperature and water abundance, between clouds and water abundance, and also normalization degeneracy in the case of the planet radius and the stellar radius. So all of this is basically telling us, look, what you found may not be as accurate as you think because the data is not as accurate as it should be. And just to finish up again, these are gonna be my acknowledgements. So I'd like to thank everyone that is here, and especially Larim for the financial support to be here. And I'm gonna leave you with my take-home messages, as I said a few times now. So we found differences in water abundances. We found degeneracies. So in summary, all of this is telling us, look, your data is not as good and you need better data. So basically, this is gonna be my main conclusions. And hopefully with James Webb data, which we're already working on as we speak, the retrievals for the same planets are gonna be more constrained. And if you're interested in all this work, I should let you know that we just submitted our paper. Oops, sorry. This is extra, sorry. We just submitted our paper, so we hope it's gonna be published soon. So if you can, please take a look. And I accept questions in any language, Portuguese, English, and Spanish. Thank you very much.
So questions over there? And then.
Thank you for the nice talk. I wanted to ask you about your abundance profiles. Are you assuming homogeneous profiles, or are you solving chemical equilibrium?
No, yeah, equilibrium and homogeneous profiles all the time, because actually when we started new studies with James Webb, we kind of saw that there is some difference, but it's still not as big of a deal for the planets that we tested that already have James Webb data. So, but for this one with Hubble data, everything homogeneous. It's a limitation, but yeah.
Thank you.
So the other question was over there, or no? No. Okay, so if there is no more questions, thanks again. So the last speaker is Anitha Raj Rajkumar. Sorry. So the title of the talk is A Comprehensive Homogeneous Investigation of Orbital Ephemeris and Transmission Spectrum of this nice planet. Okay, welcome.
Hello. Hello, good morning, everyone. I'm Anitha Raj. I'm a PhD candidate in Universidad de Atacama from Chile. So I'll be talking about orbital ephemeris and transmission spectrum of WASP-19b. So I have partitioned my talk into 3 different small parts. The first is the introduction, and then the main part, and then the side part or final part, whatever you can call it. So let me start off with an introduction about the WASP-19 system. WASP-19b is a gas giant exoplanet, and it is an ultra-hot Jupiter. When we think about the ultra-hot Jupiter, what's so special about it is they orbit their host star very close. I'm talking about the orbital period being less than 24 hours. So they are quite special. So these class of exoplanets, they have ultra short period. One of the reasons is that they orbit very close, so they have short periods. And what other reasons could there be? The other reason could be due to the higher temperature caused by the proximity of its star. This may have stripped off the planet's outer layer, which leave behind only a dense core. This might also lead to an even faster orbital period. And this scenario, we call it as an orbital decay. What causes an orbital decay? The first reason, it could be the tidal interaction. The strong gravitational interaction between the star and the planet causes a tidal bulge. So when the planet orbits a star, this creates a tidal bulge, and this tidal bulge eventually shrinks the orbit of the exoplanet. And due to this will increase the orbital velocity of the exoplanet and thereby decreasing its orbital period. So this tidal quality factor, it measures the efficiency at which the planet experiences the tidal dissipation. And also it is an important parameter for understanding the tidal evolution of the planet and its orbit. So it is very much important to calculate when it comes to orbital ephemeris study. And the second reason, it could be due to the planet's atmosphere being stripped away by the close proximity to its star, like I mentioned earlier. Or it could be due to the interaction with the other planets. This creates a gravitational influences in the system. So how can we identify and keep track of this orbital decay, which can be experienced in a system? We monitor the planet's orbital period over a time using a method called transit timing variations. So that is, we usually measure the transit time of an exoplanet and we observe it eventually. And if the orbit decreases, the transit timing will change. So that's how we measure the transit timing variation. And we monitor this with a large number of data. And we attempt to identify the rate at which the planet's orbit is decaying. So one of the best examples was WASP-12b. In the year 2020, this exoplanet has been confirmed that it is experiencing an orbital decay. And over here, you can see the decay, which is experienced in their orbit over the period of time. So coming to the main part, we have used 28 unpublished photometric data, only from the Danish telescope at La Silla, Chile. And this photometric data is being observed as a part of the MIND-STEP observations. And apart from that, we also have other spectroscopic data from the published papers. And also, we have test data. We have like 4 sectors of test data that we have used to produce results of the orbital ephemeris for the planet. And this is the high precision of the orbital ephemeris, especially the linear ephemeris of WASP-19b. Here, the blue points show the data of a Danish telescope, and these are from test data. And the other colors corresponds to the other published data. So what we can see here is, especially with the Danish data, there is a prominent decay in the data. But in order to confirm this, we need to do the higher order polynomial, like cubic or quadratic polynomial, to confirm this decay, whether it's actually a decay or something else. And also, we need extra data. For example, we have used 28 unpublished photometric data to do this, right? Which is from the year 2011 to 2023 present. But this is over a decade, but with more extra data, which will be even more accurate to tell the results. And the other part of my study is we have constructed an atmospheric characterization for this exoplanet, WASP-19b. So the black points here shows the photometric data that I've used for the orbital ephemeris study. And the blue points here are the HST spectroscopic data, which is published already. And we have modeled this using a Petit-Raytrons retrieval model. So what we can conclude here is that the Rayleigh scattering and few atomic species like sodium, potassium, and also water over here seems to agree well with the model and also the HSD data, which is already published. And the below plot is the residual of the HSD spectroscopic data. And these are the best fit parameters that we have obtained from the retrieval model. So the final part of my study is dealing with the star spots. So when the star is active, the possibility of the presence of a stellar anomaly is high. And our star, WASP-19A, is a very active star. So we need to model the star spot in order not to have any anomalies with the orbital ephemeris study. So the star spot here affects or misinterprets the orbital ephemeris. And the simplest way to correct it is by modeling them. So we have used PRISM to model the star spots. Speaking of PRISM, it models the light curve itself. And if there is a possible star spot, it models the star spot as well, along with the limb darkening. So this simple act of modeling the star spot could really save you the day, because this could really alter the orbital ephemeris values, and this will give a wrong result at the end. So not only the star spot could affect the or misinterpret the orbital ephemeris values, but also it could affect the transit depth of the light curve, and thereby diminishing any spectral features that is present in the atmosphere of the exoplanet. So we should keep track of the star spot or the possible star spot that is present in the light curve. So as for the summary, this orbital ephemeris is mainly due to, or mostly due to, the tidal effects caused in the system. And these can be noticed in our lifetime, like a human lifetime. So how can we notice this? We need to have a large homogeneous data to keep track of them. And since we are talking about the transits, if there is a star spot present elsewhere and doesn't affect or coincide with the transit, it's fine. But if the star spot is present where the transit is happening, then it's going to be a mess, and this must be modeled properly. So a bit of future work is that for the orbital ephemeris, a higher order polynomial should be verified to actually say whether the exoplanet WASP-19b is experiencing the orbital decay or not. And that's it. Thank you so much. Thank you for your attention.
So we have plenty of time for questions. So over there.
Thank you for the talk. You mentioned that the fact that you see these transit timing variations, that's evidence for tidal decay, but that could also be caused by an outer companion that's actually shifting your center of masses slowly. One evidence that breaks this degeneracy is actually transit duration variations. Have you measured that to see, in fact, if your duration is shortening?
No, the duration remains the same, but the thing is, with the orbital period, it might decrease because WASP-19b is a well-studied exoplanet, so there couldn't be any possibilities to misinterpret with a companion star or anything. So if there is a decay happening, it must be with the planet, exoplanet.
So no more questions. So thanks again, Anitha.
Thanks for the talk. Do you expect that this planet will be destroyed by tides eventually?
Yeah.
Do you know when?
When do we experience the tidal effects? Could you?
No, when the planet will be so close to the star that it will be destroyed by the tides.
It could build up the tide bulges. I did not understand the question. I'm sorry.
Sorry.
We can discuss later. If you
yeah.
want. Yeah.
One question over there.
Congrats for the excellent presentation. My question is, how fast is the orbital decay?
Well, when I compare it with WASP-12b, WASP-12b has quite a fast orbital decay, but this is not the same case with WASP-19b. Yeah, in the case of WASP-12b, this is like very quick, but even with 11 years of data or 12 years of data, we couldn't find a prominent decay in WASP-19b. So we are expecting more data to analyze more, in a better way. So I cannot conclude the decay rate. And also we need the tidal quality factor, I guess.
Okay, so let's send again to Anita and all the speakers. We have